Thank you very much, Spinta, for the wonderful introduction to ICTS. So I think we should proceed with the first lecture of the school. And our first lecturer is Professor Barry Sanders, who's from the Institute for Quantum Information Science, who's the director of IISc Calgary. And so Barry is going to introduce us to quantum information and computation. Barry. Yeah. So this is your laptop?
Testing. Good. Hear me in the back? All right. So it's a great pleasure to be here. I can do it. Okay. So getting over my jet lag, so I'm not 100% here. Yeah, it's a great pleasure to be here. In fact, Urbashi introduced me as coming from this Institute for Quantum Information Science. In fact, we've just, this is my first talk from the Institute for Quantum Science and Technology. So Calgary, we got some extra funding, we've grown, and we now have 15 faculty members, and we've broadened out. We certainly include the quantum information, but we have a number of other areas in quantum science and technology, branching into computer science, mathematics, physics, and chemistry. I thought I'd give the talk a more whimsical title, Whither Quantum Computing. That just means where's it going? So I'm hoping in the hour and a half I have to try to, it's very ambitious. I want to make sure you understand everything. I'm going to tell you what quantum computing is about, what's been done, where is it going, what are the complications, and then you'll be ready for the rest of the winter school by having that background. So the idea of quantum computing, so I'm going to focus mostly on quantum computing, not on other very interesting areas like quantum cryptography, etc. I think we'll hear something about that. And so let's begin by making sure that we know what a quantum computer is. Now, if you believe quantum physics, and I think most of you do, then everything is quantum. So the computer that I'm running this talk from, my MacBook Air, is a quantum computer. It's got a transistor in it. Transistors are quantum. So the question is, what do we mean by a quantum computer if the whole universe is quantum anyway? And the answer is that we think of a quantum computer as a computing machine that will run any quantum algorithm directly. So any quantum algorithm that's believed to be efficiently executed will be efficiently executable on a quantum computer. And I'll try to give you some more details on that. But essentially, so a quantum computer runs quantum algorithms as efficiently as they're supposed to run. And a universal quantum computer will run any quantum algorithm. We think this is very interesting because there are some cases of computational problems that perform much better by running a quantum algorithm on a quantum computer than by running them on a classical computer. So anything that's not a quantum computer that runs these quantum algorithms we'll call a classical computer. Even though this computer has transistors, we think of it as classical because we could make it out of billiard balls on a table and run it with equivalent efficiency. So one important result was Loew-Grover's, and he showed that searching a database, so you have to quantize the database, but then searching it is quadratically faster. Not only that, but this algorithm that Grover came up with was later shown it's provably faster, and so we have at least one case where there's a quantum algorithm that is better, provably better than any classical algorithm. So this proves that a quantum computer would be better in some sense. The one that kind of set the world on fire back in 1994 that Peter Shor did was to consider prime factorization. So the prime factorization can be turned to a decision problem, and then its efficiency of that decision problem can be discussed, and essentially the quantum algorithm that Peter Shor came up with and was later improved will perform kind of exponentially better than any known classical algorithm to solve the same problem. So this case is interesting. I'm putting super polynomially to be technical, but essentially we can think of it as exponentially better. And so the idea here is that factorization on a quantum computer is better than any known classical algorithm. So we don't prove it's better, but we strongly believe it's better. In this case, it's only a quadratic speed up, but it's provably a quadratic speed up. So this proves that a quantum computer can be better, and this shows that a quantum computer could be extremely valuable. And let me explain why this algorithm is considered very important. So over here, I'm going to explain why this factorization turned out to be so important far beyond science, into the realm of information security in society and so on. And the idea is that right now our world relies heavily on secure communication. And the way that secure communication works is you could think of two parties, Alice and Bob. And Alice wants to communicate with Bob. So Alice performs some mathematical calculation. I'll show in a moment. She performs a mathematical calculation. Part of her output is a string of numbers that she sends over to Bob. Bob wants to write the message, hello Alice, combines it with this string of numbers in some way, and then the result is an encrypted message, which I'm writing in hexadecimal in that form. That then goes to Alice. Alice has a private key that she doesn't share. She can decrypt it and get the answer back. And this kind of approach underpins modern public key cryptography. And the idea is that the calculation that Alice does when she sends it over is considered very hard to break. So it is breakable. It means that this kind of encryption that we use on the internet, we use for all kinds of what we think of as secure communication, is only secure in the sense that an eavesdropper or an adversary is believed not to have the capability to break it. So we make this bounded computational assumption. And there's two things. One, we assume that the eavesdropper has a limited computational power. And second, we believe that the eavesdropper doesn't have a quantum computer. And actually the third is we believe that the eavesdropper doesn't have a better algorithm than anything we know already. So there's three key assumptions to security. The second one I mentioned, the quantum computer, is not reliable because at the moment, so if we're theoretical physicists, we should believe that anything that's not forbidden is allowed. And we can't prove that a quantum computer is forbidden, therefore it's allowed, and therefore it becomes a key security risk. So the idea back in 1994, Peter Shor's result, showed that a quantum computer had a devastating impact, if it's built, on communication security. And since then, there's been no replacement algorithm for this one, in particular the RSA algorithm. No replacement has come along that shows that that can be shown to be impervious to a quantum computer, an efficient quantum computer attack. And here's the RSA. There's a t-shirt you can buy so you can walk around and remember how it works. A key point in cryptography is it's publicly known how the encryption works. I don't want to go into the whole thing, but the idea is that Alice would generate a couple of prime numbers, P and Q, and then she uses those prime numbers, takes the product, produces a number n. These prime numbers are thought of as being bit strings. Their length is roughly equivalent. N, which is the product, is known as the modulus because it's used in doing modulo arithmetic. And there's something known as a totient function, which tells you how many positive integers are co-prime with n. And then there's a number e, which is picked between 1 and that value. D is then the inverse of e. And then when Alice sends out her public key, she sends e and n. And then Bob, when he sent that message, hello Alice, would pad the message in some way, perform this calculation, send it over, and then when Alice gets back that cryptic message, she then calculates the real message because she knows D and the rest of the world don't. So that's the way it works. This is the RSA algorithm, and it's publicly known. It's very simple to write down, very simple to understand. It's nice just to do some calculations yourself to see how it works. Our security is based on this or similar algorithms, and they're not safe against a quantum computer because the factorization or discrete logarithms are breakable efficiently on a quantum computer. There are better ways of doing it. So for example, if you care, like if you're the President of the United States and you got to walk around and send secret messages through the internet, this might not be good enough. There's another approach, elliptic curve cryptography. Ashwin Nayak will be talking later, is at the University of Waterloo. That's where it was invented, right? Correct? Elliptic curve, yeah. So this was invented at the University of Waterloo, where Ashwin is from. And this one is also not secure, not provably secure against a quantum computer. So even the most secure form of public key cryptography is not secure. So the whole idea of the quantum computer then becomes immensely important, not just as a say as a physics exercise, but because our security and our assumptions of forward security depend on whether we can make a quantum computer and how it will operate. And that cartoon captures the message. Here's Alice and Bob in the cartoon, and they're trying to have a secret message. Oh, Alice, you're the one for me. And Alice says, but Bob, in a quantum world, how can we be sure? And then there's a direction to go to try to prevent. So kind of like what quantum information giveth, it taketh away, and vice versa. And the idea here is quantum information takes away the security. There's another branch of known as quantum cryptography, or quantum key distribution is the basis. And it's commercial. You can buy some system and have a way of distributing key. And the intention is that the key distributed by quantum cryptography is impervious to a quantum computer attack, in fact, against any kind of computational attack. Okay, so now we see that, this is the slide I had up before with an extra line, the Grover algorithm proved that the quantum computer was better in the sense that there is an algorithm that is provably faster than any classical version of the search. We see that prime factorization is exponentially better than any known classical algorithm, and that affects our entire world of communication security. And there's another one which has really made the world very exciting right now to physicists and chemists in particular, and this is the area of quantum simulation. And I'll show you in a moment, this is how Richard Feynman first invented the whole field. And the idea is that the quantum computer could efficiently simulate any quantum evolution, whereas classical computers are not. I don't know if people here ever read the comic book What is the Matrix or saw the movie The Matrix after it. And I always think of this. In the Matrix, not that if you don't want to know the ending, don't listen, but the idea of the Matrix is that these people live on what seems to be the Earth, and in fact they live in a simulated Earth. And the idea is that simulated Earth is almost perfect, except for certain things like deja vu and different meats tasting like chicken and various glitches that take place. But the idea is that the Matrix is an efficient simulation of the world as we think about it. And then the question would come up whether, I often think if I'm watching the Matrix, could I then conduct a set of quantum experiments and find out that I'm living in a simulated world? And I kind of think of Richard Feynman's original introduction in that way. He's asking that question. He's asking whether the world as we know it, including quantum materials, quantum field theories, etc., are efficiently simulatable in a quantum computer. Could we somehow replace the real world by a virtual world and study what takes place? So Richard Feynman gave a talk back in 1981. This is published in the International Journal of Theoretical Physics back in 1982, and it's called Simulating Physics with Computers. So Feynman, there were two papers that, actually there was a paper soon after. So Feynman's was the first. There was another one by Paul Benioff soon after, and Benioff was really asking the question, what would happen to a computer if you quantized it? Feynman was asking a much more interesting question, I think, and this is why his work is really the prominent one in the field. So the idea that he's asking is whether the universe is simulatable efficiently on a computer. You can see down here it was actually a keynote speech. So Feynman, he's very fortunate that way. He could just stand up and give a talk, and I guess somebody else would just take notes and it would turn into a paper. So I think it's something we can all strive for. Just get up and give a talk like I'm doing, ramble on, somebody takes notes, writes a paper, and only puts the name of the speaker on it. So you can see he's hit some level. So he says here, on the program it says this is a keynote speech, and I don't know what a keynote speech is. That's the very beginning of the paper. Anyway, he goes on in the paper and essentially introduces concepts of quantum computing, but a lot of concepts that are now clear to us were not clear back then. But in part of the paper, he introduces the concept of the quantum computer. This was given real substance by David Deutsch a few years later at the University of Oxford. So David Deutsch took this idea and then he said, what if you take a Turing machine and you quantize it? But the essence of it was really in Feynman's paper. So in this one, this is section 5 of the paper. And Feynman asked some questions. And I think it's important that we actually look at what Feynman said to try to understand the point. So he says, now the next question I would like to bring up is, of course, the interesting one. And it's really interesting. My whole life is now dedicated to that question. Can a quantum system be probabilistically simulated by a classical, and then parenthetically, probabilistic, I'd assume, universal computer? So that's the interesting question Feynman introduced. And that's the one he spent a lot of his later years actually thinking about. So he became absorbed in thinking about this whole question of quantum computing. And he's asking things here that are really interesting. Can it be simulated? Well, part of the issue in the paper is so the first thing is that we believe that all quantum mechanics is simulatable on a classical computer. If we do quantum Monte Carlo simulations or other methods to try to solve problems, we believe it's simulatable, we just don't think it's tractable in a lot of cases. So we try to run it, but we think that the overhead of solving larger and larger systems is beyond our capability. So probably what Feynman was talking about when he asked if it could be simulated was not whether a computer could run it and solve the problem with infinite resources, but rather it was efficient. And nowadays we think of an overhead, like the space and time cost. You know, how big a computer you need and how much time does it take to run and how those costs scale with the size of the problem. So he never said it in the paper, but he's probably thinking of the efficiency issue. And here he introduces an interesting question, probabilistic, I'd assume. So he's then, in computer science, there's a key issue about deterministic versus non-deterministic machines. And Feynman is probably thinking along the lines of quantum physics as having an inherent randomness. For example, the measurement problem. So he's allowing this computer to have free random numbers. So he's saying if you take quantum systems, if you have a computer that is classical, so it's equivalent to like a billiard ball system that you just run things to do operations, and you allow free random numbers, would it then simulate a quantum system? And he probably means efficiently, and he probably means with bounded error. In other words, a computer which will give the same probabilities as the quantum system does. So that means that if you take the observables, you know, what is the mean position x, or what is the spin of a particle, and you write down, you say, these are the observables I want, these are the expectation values, he's saying he's turning into a real problem. You know, the problem could be, is the expectation value of the position between minus 0.3 and minus 0.4. If you take the computer to be the classical kind I've described so far, not the quantum kind described in the last section, which is where he laid the foundation for Deutsch's quantum Turing machine work, and there's no changes in any law, and Feynman was extremely rigorous. I've never seen any other paper do this, but he rules out magic. He says there's no hocus pocus. So he's even allowing the magic loophole there, which I haven't heard about. Later, the answer is certainly no. So he's making a very strong statement, and we actually don't believe him on this point. He's saying that if you take a classical computer, then the answer is, well, the answer is certainly no. We think the statement is true, but it's not provable. The idea that quantum systems can't be efficiently simulated on classical computers, we all think that's so, but we don't know it's certainly the case. And Feynman gives a reason why he says it's certainly no, and he says this is called the hidden variable problem. It is impossible to represent the results of quantum mechanics with a classical universal device. And I think here, and I'm very sorry to say something negative about Feynman's great work, but in this case, it can't be correct. That the idea of the hidden variable problem being the reason that a classical computer can't efficiently simulate can't be right. I have my own reasoning on this. It goes like this, that if variables are hidden, then the cost of the hidden variables also has to be hidden. So if it turns out that that the world, like quantum mechanics, turns out to be wrong and local hidden variable theories turn out to be correct, you could still make use of the hidden variable theories in computing, and the fact that they're hidden means you'd never even observe the cost for them. So I think the argument can't be right. So, but it's interesting. So I just criticized one part, but Feynman actually had, he exhibits in this paper a lot of the deep thinking in the field. It's also interesting to go through it now 30 years later, because the field has grown so quickly that the concepts, the framework are all there to try to really make sense of this whole issue. We now have a very good handle on it, and this is the foundation of the quantum simulation branch, which is actually the subject of my 2 tutorial talks at this school. Here's a picture to show you the idea of the simulation. So you can think of this like the matrix I mentioned before in the real world. And so the idea is we have a real world, and we'll represent it by quantum mechanics. So we'll start off with an initial state psi naught, a final state psi t, where t is the time. And this is the evolution. So for simplicity, let's pretend the Hamiltonian is time independent, and its evolution operator is just given by e to the minus I t h hat. So any state could be cosmological, the state of the universe, etc. Whatever state it is, if you think of it as a unitary dynamic, then that represents the Schrodinger equation and evolution in quantum mechanics. This H is the Hilbert space. Now we want to ask the question of whether it's simulatable on a quantum computer. So here, instead of dealing with Hilbert space, just any Hilbert space, we consider a tensor product of Hilbert spaces, each one two-dimensional. So each two-dimensional Hilbert space holds a qubit, a quantum bit. This n qubit system is the size of that's the space we have in our quantum computer. So n is the space, and it's just a string of qubits. Here's the initial state, but on a computer, everything is approximated. So the tildes on top represent approximations. So here's the actual state, here's the approximated state in the quantum computer. Here's the final state that we want to get, and we want to somehow get it to be close. So remember, in a computer, almost always you get the wrong answer, but you call it right if it's only wrong a little bit. And so the idea here is on a quantum computer, if we simulate the world, we just want it to be close. But what does it mean to be close? Well, on a classical computer, we have the answer we want, the answer we got, we take the difference, take the absolute value, that's our error. In a quantum computer, we need an appropriate metric, and it turns out that there's a Fubini-Studi metric on the Hilbert space that we make use of. It behaves very nicely, so we can make use of a particular metric to talk about how wrong our answer is. And then the evolution here, the Hamiltonian has to be approximated, and even time has to be discretized. So there's no continuous variable on a quantum computer. Everything has to be discretized, and every aspect of it must be taken into account in assessing whether a simulation is efficient or not. We have to look at every single cost and all the algorithm, runtime, space, etc., to be able to assess it. I'm going to show you in a moment that when Feynman hadn't fully addressed that point, and the Seth Lloyd, who's in mechanical engineering at MIT, had a famous paper out in Science back in 1996 where he talks about proving Feynman's conjecture, and essentially his paper focuses on this point of turning a continuous time to a discrete time. So that was the aspect that Seth Lloyd focused on. Okay, so now we're going to get to those issues, but first I want to fill you in on the basic building blocks of the quantum computer. I've mentioned a little bit about the H2 tensored n, etc. And those are the quantum bits. So here are the building blocks that we need for a quantum computer. And this applies with all quantum computers. You can hear various different types of quantum computers discussed. Some can be very subtle. And what the elements are, we heard at the beginning about Shankar Das Sharma, who was here. I guess he talked about the topological quantum computing. But even the principles I talk about here still fit, even if you get to some of the more abstracted versions of topological versions of quantum computing. So the idea is we have a quantum bit, and in a quantum bit, we think of the logical 0 and the logical 1, or a superposition thereof. If you want to think physically about it, you can think of an electron spin. So an electron can spin up or down, and you can think of an electron spin down as a 0, and an electron spin up as a 1. And in a field, you can cause a precession, and a precession would take you to a superposition of 0 and 1 and change it dynamically. So you can see that there's a richness of being able to take superpositions of 0 and 1 in a physical realization like electron spin. We can also make a string. You can just imagine if you like, a trap that has a trap of single electrons, and each one's spin is 0 or 1 or superposition thereof. The string can then be prepared in some arbitrarily entangled state. So you can write down a superposition of different numbers, and then in principle you can prepare your electrons in those spin states. We don't do it directly with electrons. The best example right now is the ion trap experiments in Rainer Blatt's group, and Christian Roos at Innsbruck in Austria, and they have 14 ions that they prepare not in any superposition state, but in some very interesting ones. And then we need gates. Classically, if we have a bit, 0 and 1, we transform it using Boolean logic gates. This is normal. Boolean logic, for example, a NOT operation turns a 0 to a 1 and a 1 to a 0. And we could do XOR operations and NOR, etc. We need the quantum version for it, but the quantum gates have to be able not just to take any bit string to any bit string, but any qubit string to any qubit string. That means whatever n-qubit entangled state you have to be able to efficiently map almost perfectly, so there's an error bound, to any other entangled state. And it turns out in a very beautiful result early on in quantum information that if you have to make any universal transformation on an n-qubit string, you can always decompose it into single qubit gates, so operating on one particle in a superposition of 0, 1, and a single entangling 2-qubit gate. And this actually makes the whole field appealing experimentally. It means that experimentally, if a lab is able to generate two kind of non-commuting special gates on a single qubit and one entangling 2-qubit gate, then, and if they work well enough, then it should all be scalable up to a large quantum computer. So on an experimental level, a lot of effort goes into generating those gates, and this theory shows that if it meets a particular threshold value, then it should be scalable. And in fact, Ray LaFlamme will be here, and he was a co-author of a paper I'll mention too about fault-tolerant quantum error correction, which establishes the principles for when that's going to happen. Okay, and then a couple of other things are needed. Another one is we have to be able to prepare a zero state. In the old days, I remember when I was first using computers, I had to actually zero all my variables. Now it's all automatic. But you're always aware you had to zero everything. You don't want to start with rubbish. And so we have to be able to prepare qubits in some zero state. If you think of electrons in a row, preparing it is just a relaxation. So if you allow your particles to relax to some ground state, that's one way to prepare zeros. And you have to be able to read it out. You have to think of these particles as being a register, and you have to say, I want to read the state of the fifth particle in the register. You have to have that readout capability. When I say you have to, actually, there are different ways around it. There's a lot of clever schemes around that, but that's the idea. Okay, very early on, and David DiVincenzo back in 1995 had a science paper that laid down the whole side of implementations of quantum information. And in his paper, he proposed criteria. Now, these criteria are a little bit dated. It turns out we have different models of quantum computing that don't obviously work with these criteria, but they were very influential in the early days, and they certainly apply to particular models. Each of the criteria is several words, but I don't think like that, so I just have my anagram I remember as SICM, and then I never forget, because often you have to, you walk around, you have to remember these things all the time, so I just remember that. And so the idea here is DiVincenzo introduced 5 criteria. He said in order to judge whether a technology is a good candidate for a quantum computer, we have to ask the following 5 questions, and the answer has to be yes. And the first one is scalability, and this again fits with what Ray LaFlamme did, the fault-tolerant quantum error correction. The idea is that if you can make a few qubits and a few gates, you have to be able to grow it into a large computer efficiently. So if your cost of correcting errors and addressing errors grows exponentially, it kills the whole purpose of the quantum computer. So scalability is essential. Initialization is preparing all zeros. Coherence is the idea that decoherence is very bad, so you have to make your system somewhat isolated from the environment so that it won't decohere too quickly. Basically, if you're going to do a gate, you want to make sure your gate time is much faster than your decoherence time. And then universality is the idea that you can make any unitary transformation, which in many experiments corresponds to making single qubit and 2-qubit gates, and that's it. And that would satisfy the universality criterion. And finally, the measurability is you have to be able to measure whether the fifth particle is in the 0 or 1 state. And since then, there were various other criteria that came along that added to DiVincenzo's criteria. I've seen 10, but I'm only putting 7 up here. I think these are the 7 that people now think about. And these have political overtones as well as good scientific ones. One of them is interconvertibility. And the idea is that if you have a qubit, let's say you have a qubit which is the electronic state of a trapped ion, and then you want to convert that to a photon, or you want to transfer that to a nitrogen vacancy in a diamond, and transfer that to nuclear spin. The idea is the qubit needs to be convertible to different forms. So some people argue that no technology will ever satisfy all of those, and so the technology has to have an interconvertibility, that qubits have to be transferred from one medium to another. This used to be called hybridization. Now if you see the term quantum interfaces, this is what they're talking about, and it's very big. Nowadays, if you write quantum interfaces in a grant application, you're sure to get your money. So that's one. And the other one is the flying qubit, and the flying qubit had a political overtone. At one time, it was used as a way of arguing for funding away from solid state into more atomic stuff and photonic. And the idea is that if your qubits don't move, you won't have scalability. And so the idea is that there had to be a form of qubit in the system that could be coherently transported from one point to another. So those are examples. Okay, let's go into the mathematics. Now the mathematics of quantum computing is not like a lot of areas of theoretical physics. It's actually not that hard. I've had, in the early days, I would get undergraduate students, give them problems. They would solve non-trivial problems. We would write up papers, and all they needed to have was like a second-year linear algebra. Nowadays, it's kind of much harder. There's a lot of theorems that you have to know, but it's really a lot of the stuff is just linear algebra. So in that sense, if we take our qubit, we can write the 0 state as a 2-component vector with 1, 0, and our logical 1 state as that vector 0, 1. And actually, I don't know, a lot of you probably heard of David Mermin. He wrote a famous book in solid state physics, and he's got a very good book on quantum computer science. That's what it's called. And he wrote a book a few years ago. It's about 130 pages long. It's not very long. I strongly recommend it. And he decides he's going to teach quantum computing to computer scientists. And in fact, everybody I know who's a physicist loves the book. So his book failed in the sense that it's the physicists who especially love it, as far as I know. And he poses the following question. He builds up computer science as being a vector space problem. So he says, imagine that all bit strings are just integer lattice points in an n-dimensional space. And then he poses quantum information as saying, instead of restricting yourself just to the basis elements, allow basis vectors to add to form new elements. So he kind of builds up quantum computing that way. It's very nice. So I'm following a little bit of that approach here. Then, if the qubits are just 2-component vectors, 2 qubits would have 4 components, 3 qubits would have 8, 4 would have 16, etc. So then gates can be written simply as matrices. The Hadamard transformation is just a normalization factor, and it's 1, 1, 1, and minus 1. So it will take, if we take the 1, 0, which was the logical 0 state, and multiply it, it turns the logical 0 to a superposition of 0 and 1. It turns the logical 1 to a superposition of 0 and 1, and there's a phase change. So 0 goes to the 0 plus 1, 1 goes to the 0 minus 1 state. And it turns out that for universality, one universal set is just 3 gates. So if we have this gate and we add to it an R, this is known as a pi-on-8 gate. This transformation leaves the 0 state unchanged, but puts an odd-looking phase factor in front of the 1 state. If we can do that, and we can do a controlled NOT operation, and the controlled NOT, you can see an identity matrix here, and a sigma x Pauli matrix, which is a NOT operation here. So this matrix says, if your first qubit is in a 0, don't change your second. If your first qubit is in a 1, flip the second. In computer science, this would be the XOR. If these 3 can be done experimentally well enough, that's a universal set, and then you just need those 3 gates and you scale up. Now, what we do, it's too much to write all these matrices, and worse yet, you can see that the matrix size grows exponentially with the number of qubits, so we can't write those down. So we borrow an approach from computer science, and instead we write down circuits. And over here, this is the way it works, and if you're going to follow on in this field, it's good to know this kind of picture. This is how we often work. And so the idea is a qubit is simply written as a horizontal line. And there's a time axis. It runs from left to right. So this wire, we call that a wire. This wire just represents a qubit evolving in time. And then it hits a box. And so the wire is a 2-component vector. And the box is that 2 by 2 Hadamard matrix. So when it hits there and goes through H, it turns 0 to a superposition of 0 and 1, and 1 to a superposition of 0 and 1 with a sign difference. This is that R matrix. And here, this is the controlled knot. It operates on 2 qubits. So we have a wire that's a 2-component vector, a wire that's a 2-component vector. They can be entangled. This is a controlled knot. A black dot means that this controls that. So the state of this, if it's in a basis element, won't change. Of course, in a superposition it will. And this is a knot operation. It will flip. So every unitary transformation on n qubits can be decomposed into a polynomial size sequence with respect to n qubits, a polynomial number of these kinds of gates concatenated together. And I'll show you an example in a moment. But what I want to do is, to show you how the circuit works, let's have some fun with it. What is the favorite problem every quantum physicist likes to talk about after work? And you go and sit in a coffee shop or something. It's quantum measurement paradox and Schrodinger's cat and stuff like that. So let's simulate it. If we can simulate anything, we should be able to simulate Schrodinger's cat. So I claim that this circuit is going to simulate Schrodinger's cat, and in doing so, you'll get a feeling for how the circuit works. So here we have 2 wires corresponding to 2 qubits, Hadamard controlled knot operation. And you can see that if 0 goes in, it turns into a superposition of 0 and 1. The controlled knot says if that's a 0, that doesn't change. And if that's a 1, that flips. So it takes 0, 0 to a maximally entangled 2-qubit state. To see the connection with Schrodinger's cat, consider the following. The idea of Schrodinger's cat is that there's a radioactive particle sitting in a box, and the radioactive particle has a nucleus, and the nucleus is going to undergo an alpha particle decay. And in one of the nuclear models, the way we can think of alpha particle decay is we could just think of an alpha particle, it's a bare helium nucleus, as freely moving inside the nucleus, and then there's a potential barrier on the outside. You write down the equation of a particle bouncing around inside a finite spherical potential. It's not that it's probabilistic that it emits in a superposition state of emitting and not emitting. So if you weighed something like the half-life, then the alpha particle would be thought of as being in an equal superposition of decaying and not decaying. That's what the Hadamard is. So if you take an alpha particle in a nucleus and you wait on the order of a lifetime, then that's a Hadamard transformation. That's this gate in the Schrödinger cat system. And the result here, when it comes out, is it's a superposition of being inside or outside, 2 states, so it's a qubit. So that becomes a qubit. The cat can be alive or dead, and if the cat's alive, we can call that a 0, and if the cat's dead, we can call it a 1. So here, the input state is the nucleus without the alpha particle decay, and the living cat. Then the Hadamard transformation takes this to a superposition of decayed and not decayed. Then the control operation is that detector click. If it decayed, the detector clicks and does a not operation on the cat. Well, if the cat's a qubit and it can be alive or dead, the not operation turns a living cat to a dead one and vice versa. There's subtleties with the Schrödinger cat paradox where you have large systems, but in this simplified model, that's what we can think about. And so the living cat has a not operation and now it's dead. But it's entangled with whether that came through or not. So you see, the Hadamard was just waiting long enough, and the controlled knot was that detector click. And so the idea is simply that the alpha particle, the controlled knot is just the alpha particle that hits the detector and does a knot operation on the cat, kills it. And so the result is that we either have an undecayed nucleus and a living cat, or a decayed nucleus and a dead cat, and it's in a superposition. So that's an example of how that circuit simulates this problem. So I hope that's clear then. That should give you a feeling for these circuits. Now, the problem is that in quantum computing is that nothing ever works perfectly, even the quantum computer. So I want to give you a feeling for error correction. Is there going to be error correction talk, Rabashi? Okay, so this just kind of sets a bit of the framework. And I can tell you back in 1989, 90, 91, I was a postdoc with Jared Milburn in Australia, and we were working on quantum computing, and none of our papers would ever get accepted. And I had one paper where we sent a paper, it's to Physical Review A, which I'm now an associate editor of, so it's kind of funny for me. And back then, the referee of our paper was Rolf Landauer, who's famous. I always think of Rolf Landauer as the guy who really solved the Maxwell-Demon problem. And he was so incensed by our paper, the idea that you could do quantum computing, and this is the early days of email. He sent the email directly to me and copied the editor of PhysRev. This paper should never be published ever anywhere because quantum computing is impossible. And it was very interesting back, and I gave up, actually. I gave up. It wasn't until a few years later when quantum computing came back that I tried to get back in the field. And then, the thing that eluded us and everybody else at the time, and Landauer was absolutely right in being hypercritical, was he said that quantum mechanics is too fragile. That if you try to do the exquisite control of quantum systems, it's not going to work because there's kind of this exponential overhead on doing anything quantumly. And we physicists had no clue about how to get around that kind of problem. It was true. We kind of thought about it and hoped one day people would be able to get a handle on these exponential problems, but it was a problem that we just accepted, and that's why I gave up back in the early 90s. And then it was the same Peter Shor that did the factorization. So Peter Shor created this whole revolution in 1994. Not only did he show that a quantum computer could solve a problem that completely destroys our information security. So to a physicist, destroying the world is just as exciting as making it better. So he showed that that could destroy everything, but also he showed that the fragility problem should go away. And he took a page out of the book of information theory, which is something that we physicists should have learned about, but it's not part of our education. And so the idea of quantum error correction can be related to error correction. So suppose that this room was really noisy, and I'm talking to you, and you can't hear every word I say, but I repeat the word. So if every word I say 3 times, so I, say, da, same, word, 3, times, and some of them are blotted out by noise, and you know that's the code, you can still figure out what I said, right? So that's kind of a concept of error correction, that you don't wait for the noise to come in and delete things. You make a code, send the code out, and then the deletion is efficiently fixable. And we use that in all forms of communication in noisy systems. And this is what Shannon's theory tells us, what the limits are. It all relies on coding. And this is something we physicists didn't get 30 years ago, 25 years ago. And Peter Shor came along and he said, well, what about thinking of the following? We'll do this. So he considered the repetition code, saying the same thing 3 times. But how do you do it in a quantum system? So you take the wave function. It's a superposition of 0 and 1. But now we don't want 0 and 1. We want 0, 0, 0, and we want 1, 1, 1. Okay, that's the 3 times. You do this gate, controlled not. If this is a 0, don't change those. If this is a 1, change those. And the output is a superposition of this repetition. So that becomes a quantum version of one of the simplest notions of coding theory. However, it's not enough to protect quantum information. Remember I told you that like the Hadamard made a superposition of 0 and 1 or a minus sign. So we don't just want to protect the 0 and the 1, we want to protect the relative sign between them. And so what Peter Shor showed was you could protect the sign by writing that same controlled not, but appending it with a Hadamard in each one. So he had one code to protect the 0s and 1s, and another code to protect the plus and minus. And in a dual space, it turns out that protecting the plus and minus is as though you're working with 0 1s in what we often think of as a Hadamard basis. But then he showed another important thing. He showed they can be concatenated. So he said what you just need to do is combine. You first correct for bit flip errors, then you correct for phase flip errors, and he showed that he got a 9-qubit code. And later we understood that this is a form of 913 codes in information theory. So Shor showed this idea that you could correct for the errors, you can correct in different ways, and you could just put code words in code words. And then it was quickly realized that it's almost a trivial extension of code. So the codes that were first done were almost a trivial extension of codes from information theory, which could be mapped over into quantum circuits that would be able to do things. It's not trivial anymore. There's a lot of hard problems. But in the early days, that's how it was. And the most famous code, and this will come up during my talk. I'm going to show you something about this. One code came up, which is the Steen code. And the Steen code, so Andrew Steen is an experimental ion trapper at Oxford University in the United Kingdom. And he came up with a circuit and a plan for protecting bit and phase flips. It's better than Peter Shor's in two ways. One, it only requires 7 qubits instead of 9. And another way is it's known as a transversal code. I'll say something technical in case anybody knows what I'm saying. But the idea is that it turns out that certain operations live in a Clifford group. Clifford group is a normalizer of the Pauli group. And those operations, it turns out that if you work in the code space, the gate you want to do is just operates individually in the qubit. So it's kind of trivial to map Clifford gates, which are most of the gates you would do, into the code space. Okay, enough of that technical sideline. It's a beautiful code in two ways. And these, I didn't discuss the measurement side, but these are 6 ancillary qubits that are used to be able to do measurement. It turns out that in quantum computing, you have to keep track of everything. If you're not careful, you can slip in an exponential overhead where you're not looking. So even the idea of using these even measuring these qubits to find out what went wrong and correcting them, you need to recycle those qubits. So it's the ultimate environmental exercise. You can't throw anything away. You have to recycle everything. Okay, so the Steen code is the one that experiments plan to use. I should point out to you that our ability to do quantum computing in code spaces is at a very, very early stage. I haven't yet seen an experiment that does a good quantum gate operation on a single qubit in a code space yet. So we're still at a very early stage in terms of doing protected quantum computing. But the one that people would aim for is the Steen code. It's thought to be the one with the lowest overhead. So once we start getting to fault-tolerant quantum computation, we'll probably be working in that code space. Okay, so that gives you the quantum error correction background. Now I want to get into the implementations. How are we going to build it? So, we're talking a lot about a quantum computer, but we can ask the question what it's going to look like. So first, I want to show you why it's not a good question to ask what it's going to look like, because you could ask the same question 100 years ago. So if you understand Babbage's work from the 19th century, the idea that there could be computers, or you learn about Turing's work, so I heard there's going to be the Turing lecture series. So Turing's work, that there could be a Turing machine. What is it going to look like? How could this machine operate? By the way, if anybody wants, if you go to YouTube, there's a Lego Turing machine. Lego, the kid's toy? And so they build these Turing machines out of Lego. So you can watch a YouTube video on Lego-based ones. I want to get one of these. And so so you can build a computer out of Lego. Anyway, that's the point. But in those days, if you look back at the Manhattan Project, when the United States was building the capability of nuclear weapons, computers became extremely important. What did they use? Well, they were using vacuum tubes. A lot of error correction was somebody running around pulling things out and putting other vacuum tubes in. So this is a picture of a vacuum tube triode. So a computer was just a big system with these vacuum tubes all over the place. When it moved over to solid state, there were germanium transistors, and the silicon transistor emerged a bit later. And so even the idea of what would be the physical medium for a classical computer, which is easier in some way to build than a quantum computer, even guessing what medium it would be was not known. Experiments had to be done in various areas. The same applies in quantum computing. So I've gathered a few pictures here to give you a feeling for different technologies. It's not exhaustive, but different technologies for a quantum computer, and then I'll concentrate on one in a moment. This picture is from an article in Nature by Bruce Kane, who suggested taking phosphorus and silicon. Is that, Steve, are you talking about the phosphorus and silicon? Yeah. Okay, so this is related loosely to what Steve Lyon is going to talk about. And the idea is to have phosphorus and silicon. So this idea kind of merged concepts from NMR and ion trapping. And the idea was to make use of nuclear spin, but in a solid-state system. And I'm going to show a movie in a moment. This concept, Bruce Kane, when he wrote the paper, was living in Australia at the time, working at University of New South Wales. He's now in the US. But when he wrote it, this paper inspired a lot of the Australian work you mentioned, Urvashi, Michelle Simmons, who works in this area. So I'll show a movie that shows what their concept is to give you an idea. That was actually a very big proposal at the time because silicon, of course, is a huge investment. You know, the silicon industry is giant. And the idea that quantum computing could leverage off the knowledge and even foundries for silicon chips was quite revolutionary. This one is from a paper that came out, I think, 2001, Kielpinski, Wineland, and Monroe. Wineland is the Dave Wineland who just won the Nobel Prize in December. So he's a co-author of the paper where this appeared. And the concept is to have trapped ions. Now, when you trap ions, ions are charged, so they're held in place by an electric field. These are all bits of metal that control electric fields. So a usual ion trap has the ions completely stationary. Remember what I said about the flying qubit? I said that that's one of the additions to DiVincenzo's criteria. So one of the criticisms would say this scheme was the qubits are stationary, and the ion trappers said, okay, we need to start moving ions around. So by playing with these electric fields, the idea is you can have regions where you do gates on ions, and this is a memory region. So you can shuffle ions. The concept is to shuffle ions whose qubit is a superposition of a ground and excited state, move them between different areas. So that concept, which was out in Nature 2001, was a concept that allowed ion traps to have a flying qubit. The technology is still not mature. The idea that you can take an ion and transport it and preserve the qubit is still under development, and it almost certainly has to work in some type of code space. This is the nuclear magnetic resonance concept. Over here, in liquid state nuclear magnetic resonance, the idea is that there would be some molecule. Early one was trichloroethylene, and it sits inside a test tube, and there's two magnetic fields. There's a Helmholtz coil, and so there's two magnetic fields, one a DC magnetic field, the other an AC magnetic field. The DC magnetic field simply lifts degeneracies, so your up and down states can be energetically different, and your AC field has a frequency that's tuned to bring it in and out of resonance, so you can cause one qubit to precess, and you can take advantage of two atom interactions within the molecule to do two qubit gates. And Ray LaFlamme will be talking about this. So this nuclear magnetic resonance scheme will be discussed at this school. This is the idea of quantum dots. One of the earliest proposals was, again, by David DiVincenzo. So in his 1995 science paper, he talked about NMR, but later he did work with Daniel Loss, who's now in University of Basel in Switzerland. And David's actually he left IBM. He's now in Aachen in Germany on the Netherlands border. And so the idea was to try to make use of quantum dots on the surface to be able to manage qubits. The idea is to trap an electron inside a quantum dot, and its spin, remember I talked about at the beginning, the electron spin? That would be the qubit. So, and then over here, this is a typical, just a small snapshot view of an optical lab, like what you're setting up, Urvashi. And the idea, these look very, very messy. It's got like optical tables with all kinds of things sitting on it. And so the optical experiments are also very promising. So these are a few of them. But I told you it's not an exhaustive list. I'll show you another one. Turns out that nowadays, like I would say, if you look at the real cutting edge, the three winning areas at the moment are the optical, the ion trap, and the superconducting qubit. And here I took a picture from one of the Nature papers on this. Thaddeus Ladd is the first author. A few of them wrote a paper on quantum computer technologies. And this one makes use of a superconducting Josephson junction. And the superconducting Josephson junction, when plugged in, gives you an electrical circuit that has a nonlinear inductance. So when we make electrical circuits, we often think of these as linear. We have inductive, capacitive circuits. There's a resonant frequency, etc. The Josephson junction winds up giving you potentials, gives different potential wells. If they're small enough, they're quantized. They have quantized energy levels, and you can select out a two-level system like you do for an atom. And so these things are moving remarkably quickly and very successful. Another area that's very hot at the moment, especially in the quantum simulation that I'll be talking about in my more specialized tutorial sessions, is an optical lattice. This represents a two-dimensional beams. They're beams of light that cross each other, and the atoms are held in place by dipole gradient forces, and then by manipulating the lattice, you can cause atomic collisions to entangle them. And this I took from Philip Walter, who's got in Anton Zeilinger's big empire in Vienna. Philip Walter has these experiments going on. His paper was just out in Nature a few weeks ago. And this is an optical interferometer. It's done, I think, silicon waveguide. So there's now these solid-state waveguides for multiphoton interference. I'll be talking, if people are at the conference next week here in Bangalore, I'll be giving a much more detailed talk on these experiments. Okay, so that gives you an idea of the different technologies. And what I want to do is to show you a bit of a movie. Now I still got, how much time have I got? Half an hour, okay. So I'm going to show you a movie that I made a few years ago. It turned out that there was a point where the solid-state quantum computing was running into a financial barrier, and I talked to some people in the US, and I said, well, if you give me $50,000, I can make a nice movie that will help you get more money. And they believed me, and I made the movie, but they can't tell me if they got the money. I'm not a US citizen, so I actually don't know. I can't learn what the effect was of what I did, but as long as I got paid, I was happy. So I'll show you the movie that we did. The idea is to work with the phosphorus and silicon. You'll see this in the movie. This represents a phosphorus atom living inside a silicon substrate. Here's the phosphorus nucleus. The idea is that when phosphorus lives in silicon, there's some sort of lattice spacing, and there's a 0.5 nanometer scale inside the silicon surface. There's a Bohr radius, which is the Bohr radius of the lowest orbital for the electron of the phosphorus. And it turns out that if you take silicon and treat it as some sort of dielectric background, the Bohr radius is 2 nanometers, which is huge. And then the idea is simply plant phosphoruses in the silicon just far enough apart that it can be influenced by its neighbor and take advantage of that to do 2-qubit gates and do precessions to make 1-qubit gates. So I'll play that movie, but I'm going to have a dark room. The most important light is here. That's good. Okay, thanks. So I'll play it and I'll pause as I go. But the idea here was, so I'll just mention a couple things first. So obviously it's about the solid-state quantum computer in silicon. And the idea here is based on notions. So the current effort is based on what they were doing in Australia. And the current effort no longer matches exactly what the movie is. So it's a little bit dated, but it will give you the concepts of what their plan was a few years ago. So of course the idea was to get funding, so you can't just assume that everybody cares about the physics. So you have to start off with a problem, and the problem you start with is to find the prime factors of a 2048-bit number. So if you go to a particular funding agency in the US and you want lots of money, you have to tell them a problem that they care about. And the factorization is important exactly for the reason I told you at the beginning. Remember I told you about n equals pq and so on? So the idea is to find the factors efficiently. That's what they want to know. So we consider the 2048-bit number. We point out that a supercomputer would take millions of years to break it. Quantum computer is estimated to take only minutes. In fact, we did the calculation more carefully when the movie was almost done, and we discovered it would take about a year, but technically a year is just minutes also, so we didn't go and make the expensive change. And then, and so the idea here is the following. This represents a board for computing, and over here is the quantum chip with our serial number 137.035, blah, 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 which I'm sure you know. And we dive in, and this takes us to the quantum chip. Now, in the quantum chip, the idea is that these are rows of phosphoruses, So this is the quantum register. And in this scheme, the qubit is the electron spin for the phosphorus, each of the phosphorus ions. No, neutral phosphoruses. So every blue light you see represents a neutral phosphorus, and there are other phosphoruses that don't hold that extra electron. And all this black space is there because if you plug all the electronics on, it generates heat, and you need lots of space in between because you have to have things come in to control it, and you have to have heat. You have to be able to dissipate heat. So that's the concept for the full-size quantum computer based on phosphorus. Here's that nucleus of phosphorus. This is the electron cloud. These yellow dots are the silicon. So the phosphorus lives inside the silicon substrate. Remember, these are about half a nanometer apart. The Bohr radius for that ground state electron is about 2 nanometers. And this object here kind of looks like a moon. This is going to represent the spin of that electron. So we have an electron cloud. That shows the electron location probability around the nucleus. And this represents the spin of the electron. And then remember what I said, that you have to be able to prepare the state in 0. So what you see here is that moon was covered by some dust. And the dust represents the spin being completely unknown. It's a uniform probability distribution. A magnetic field, which is hard to see, but there's lines going, vertical lines, that represents a DC magnetic field that lifts the degeneracy, and then the electron would relax on the scale of a second into zeros. So that step with the DC field relaxed all the electrons into the ground state, so we've done our initialization. Now what you see, I'm not sure you can see this very easily, these horizontal lines are the AC magnetic field. The AC magnetic field causes the electron to precess. So you're now seeing electron spin precession inside that AC magnetic field, and that precession in this, also when Ray talks about nuclear magnetic resonance and so on, that precession is what has to be controlled to be able to affect a gate. And all kinds of things are precessing at the same time. So it's a complicated problem. One thing that we do mathematically is we try to simplify the calculation by going to a rotating frame. By the way, I'll mention here, you see these interference fringes? So when you solve Schrodinger's equation for a hydrogen atom, and you do an s orbital, it's just spherically, it's rotationally symmetric. But because of the silicon crystalline substrate, these have interference fringes. Turns out that the overlap of the electron cloud with the nucleus is critical for controlling hyperfine interactions. And those fringes, we kind of thought about a lot when we made the movie. Those fringes actually make the problem less stable than we thought initially. Okay, so what we're going to do, we're rotating it. So mathematically, to simplify the calculation, we go to what's called a rotating frame. So I'm just representing that rotation here. And by going to a rotating frame, the evolution of the electron, the precession in the rotating frame, is now very simple. It wraps around. But here, you saw a flash of light a moment ago? So what you'll see is that there's flashes of light. It turns out that the electron, even after going to rotating frame, is still precessing around that axis. But we need to have the electron just in the 0 state. So if the 0 state is spin up, we have to control it stroboscopically. So it has to be a periodic control, so it's effectively only in the 0 state. So you'll see a flash of light again now. So that's the idea, that we need the precession, and then the flash of light is the timing control needed to say that we actually prepared a 0. So you can see even preparing a 0 is non-trivial in a magnetic resonance scheme. This is now the electric field. So these blue lines represent an electric field. So the idea is that magnetic fields are global, but electric fields can be done locally. So we have a local electric field, and the effect of the electric field is to distort the electron cloud. And the control in this scheme is hyperfine splitting. Now, hyperfine splitting in an atom is due to overlap of the electron cloud with the nucleus. So by using an electric field, we control the amount of overlap, and therefore we're able to shift 1 qubit in and out of resonance with the magnetic field. So the magnetic field is affecting every qubit, but we only wanted to do a gate on one, and so we use the electric fields to choose the one that will be in resonance by manipulating that cloud. Okay, and then what happens is when it's in resonance, it precesses away. Remember, it was stuck around that axis, then it precesses away. Now, there's another subtlety here, which is very important. I said about getting something to 0. The problem is every qubit in your system is undergoing a precession. So this moon here represents all the qubits you don't touch. And this represents the one that you want to do a Hadamard transformation. So you want to take it from the 0 state to a superposition of 0 and 1 on this Bloch sphere. And meanwhile, all the other electrons have to go back to here. Because, so in mathematics, it's a condition of complete positivity, that we have to have everything else in the universe, our quantum computer universe, go back to 0. This just did a Hadamard, but every other qubit in our quantum computer is now in a superposition of 0 and 1. So it didn't work. So we have to be able to take that into account. And over here, the idea is that it's wrapping around, and then we get our Hadamard now, and all the other qubits were back to 0. So when you do a single qubit gate, you have to be able to, everything has to be properly timed. The equations all do this, but it's nice to see the picture. Now I'm going to show you a 2-qubit gate. This is the control NOT operation. And now in Loss and DiVincenzo's scheme back in 1998 or so, they suggested a way of doing a controlled NOT, and it used square root of swap operations. So a swap operation you exchange. In a square root of swap, you only go half the time, so instead of exchanging, they're in a superposition of having exchanged and not exchanged. Because of the subtlety with all these other qubits in the quantum computer, it turns out that we can't use the square root of swap, we have to use the 4th root of swap. So you're going to see 4 of those operations and 5 single qubit operations to do a controlled NOT. So here is an electric field that caused a single qubit rotation. Now these ones have an electron-electron collision for the 4th root of swap, another single qubit operation, another 4th root of swap on 2, another single qubit operation, another 4th root of swap. Oh, what happened? Yeah, that was it, right? And then another single qubit, and then we're done. Okay, so that's the way to do a controlled NOT on the physical qubits. Now we have to be able to do a readout. So the qubits are over here, and over here what we want to make use of in this concept is a single electron transistor. It can measure the passage of a single electron and use a nanoschottky reservoir and allow the electron to decay into the reservoir, but it can only pass the barrier if its electron is spin up and not if it's spin down. So the idea is to have a readout based on that. And there's a scheme here where the electrons will tunnel through. It's too hard to see, and it's not dark enough, but there's a set of phosphorus ions, and the idea is to do a coherent transport through a set of phosphoruses to the readout region. And over here, there's a beam, and then the electron has quantum tunneled over to here, and then it's going to decay into the nanoschottky reservoir past a single electron transistor only if it's spin up, and this one we prepared spin up, so it worked. And then it lands in the nanoschottky reservoir. So if the electron lands in that box, we say it's 0, and if it didn't, it's 1. So now you see the measurement phase. Okay, so that's the physical implementation. Now I'm going to take you to the code space, and this is the part, a big challenge for quantum computing in the coming years is to work in code spaces, which we physicists don't want to think about. We're having enough trouble without code spaces, but it's got to be done. So I'm going to now show you the operation in first-order quantum error correction using the Steen code. And I'll show you why the Steen code is beautiful. So over here, in the Steen code, remember we took 1 qubit into 7. And remember that the Steen code had 6 ancilla qubits. So to do 1 qubit operation, you need 13 qubits. But in order to control for that precession of all other qubits, we actually need 7 ancilla. So for 1 qubit, we need 14, and we're doing a controlled NOT, so we need 28 qubits. You got it? So Steen says we're doing a 2-qubit gate. Each qubit goes into 7, and there are 6 ancilla for each one, and an extra one to correct for global precession. So we have 28 qubits. So you'll see 28 blue dots here. Each blue dot corresponds to the phosphorus carrying an extra electron that has spin. The spin is the qubit. And there are black dots, well, very light dots I'm sure you can't see. I can see it here. And these are the phosphoruses in between that enable coherent tunneling. And you're going to see a dance. I think of this as a quantum error correction dance. So the shuffling that's going on here is 48 steps to do 1 controlled NOT operation. In fact, before we released the movie, the guys who figured out this one actually patented it. So our movie release was delayed 3 months because the patent had to be filed. So this dance was a patented dance. Okay, so what you see is this is the gate region, just like with the ion trap. and outside is the preparation and measurement region. So you can see that this is, there's an inside gate region and an outside preparation and measurement region. They're going through the steps. I'm going to stop it when we reach the interesting Steen feature. Boom. See that? This, where they paired up, this happened 3 times in the movie. The controlled NOT operation is one of these Clifford operations I mentioned. In Steen, the Clifford operations have the property that the gate in the code space looks like a gate on the physical qubits pairwise. It happened 3 times in the movie. 1 for the preparation stage, 1 for the information processing stage, the controlled NOT, and 1 for the measurement stage, which is the one we're at. So these things all dance around, and we have our quantum computation. So the C-NOT is done. Oh no, that was the information processing. That's the measurement one where they pair up. And that pairing up is why experimentalists really like the Steen coding better than everything else. Now we just pull back, and now you know what these blue dots were. And now we have the movie. So any movie should have a climax. So now this is the climax of the movie. Remember, the purpose was to break a 2048-bit number. It turns out that for a quantum computer doesn't always get the right answer, but it takes on average 4 guesses to get it right for this size problem. And so here you can see 4 guesses coming out, and the quantum computer output after all the measurement are just strings of bits, and that agency wants it to crack a code. So we'll see it. We send one of the guesses, put it through a classical computer, and see it. Here's the code, and it cracked it. So it's a happy ending. Okay, and then, right. So then I'll just show you who did it. So I put it together, hired some people for it, and I worked with Austin Fowler and a bunch of people in Australia. Bob Clark, Glenn McWright, U.S. Army Research Office paid for it. So that's the idea. Can I have the lights on again? Thanks. Okay, so that gives you one example. And as I mentioned, that example is not, it's got certain problems. The electron readout through the nanoshocky reservoir, et cetera, turned out not to be feasible. But the movie does give you a sense of the complex endeavor to hit full quantum computers. We're not close to it. So I often like to joke that the movie I've got is so far it's the only working quantum computer at this point. So I'm doing like Feynman, I'm simulating it. Okay, so that gives you an idea. Then I got a few minutes left. So now this is kind of the introduction to the quantum simulation area, which I'll go through more technically later. You've seen this slide already. So I'm going to take us back to Feynman's notion and show you what's going on in the quantum simulation field, which has got a lot of very exciting work that's connecting strongly experiment theory and is leading very quickly to breakthroughs. Often I like to think of, so my friend Terry Rudolph, who's at Imperial College, he calls this the quantum singularity. Well, it's quantum computing singularity. So he says, let's consider the following issue. Suppose not that we want the full scalable quantum computer, but we want a quantum computing machine that will answer a problem that at that time couldn't be solved by all the classical computers in the world connected together. So can we reach that point? So not the point we have scalable quantum computing, but can we answer a problem on a quantum computer that will not be verifiable on all the classical computers of the day? And we're actually heading very much toward that point. I think that we're getting close. If we set that as our goal, we're moving in that direction. So I'm optimistic that I'll live long enough to see that. Okay, so the idea of the quantum simulation originally was the idea of trying to understand condensed matter physics, which has a lot of challenges in trying to solve problems. And I just put up a couple of examples of quantum materials. One is the levitating superconductor. And of course, an outstanding problem there is whether the theories for high temperature superconductivity are valid or not. And they're not tractable. A lot of them aren't tractable, so we don't know. And here's a superfluid. This is a superfluid helium that appears to be leaking out of a closed glass jar. And this area was pushed forward by Seth Lloyd. Seth Lloyd, I mentioned, was the one who stated that he proved Feynman's conjecture. And Seth, about the same time, 1996, also saw the value of going into quantum simulation. So he had a beautiful paper out with Dan Abrams, also at MIT, and they had a paper that's called Simulation of Many-Body Fermi Systems on a Universal Quantum Computer. So the question they considered was, so first they take it as obvious that a bosonic field theory can be simulated on a quantum computer efficiently, but if a quantum computer is going to simulate everything, it should work for fermions. And I blew up the equations. Here's the Hubbard model, here's the Bose-Hubbard model, which is the bosonic version, and they essentially lay out in this paper how to turn the Hubbard model into a quantum computer, into an algorithm, so solving that into a quantum computer algorithm, and they say in order to accommodate fermions using a first quantized Hamiltonian, an efficient quantum algorithm for anti-symmetrization is given. So that was kind of the hard part of the problem, and they show that a quantum computer could efficiently simulate fermionic systems not long after anyonic systems were also done. So the idea that a quantum computer could efficiently simulate fermions and even anyons was interesting. Nowadays, it's kind of interesting. We flipped the problem on its head because we heard about the Majorana fermions, etc. And so we're getting to the point where we might be able to use anyonic systems to simulate as well. So it's kind of nice that the thing we want to simulate is also something we can use to simulate as well. So this whole simulation area has become very hot. There's a nice paper that came out in 2009 by Baluta Nori, Science, and it's a review article. It talks about, it's called Quantum Simulators, and in it they just talk about different technologies that are especially promising if we want near-term quantum simulators without quantum error correction. So we forego scalability, and here's the neutral atom lattice I put up earlier. This would be a cavity quantum electrodynamics example with atoms between mirrors, and a more complicated one using a photonic crystal. And then there's the trapped ions, and it could be in a line, it could be in a square, it could have some other setup. And these experiments are actually starting to happen where you want to be able to make the ions in some interesting thing like a Kagame lattice, whatever, you know, those kinds of topologically interesting structures. And then they also pointed out different ones with electrons floating on surfaces or using quantum dots. So in the article, they pointed out these technologies as particularly promising. That was 4 years ago now. So things have moved on. There are different promising technologies, but it's a good article to read on that. And so that gives you a feeling. Again, I'm going to get into the quantum simulation more in my lectures, but now I just want to go crazy and just talk about some of the things that people are looking at for what's called quantum information inspired. So one of the things that happens in the quantum information field is we're focused on things like building quantum computers, doing quantum cryptography, etc. But there's a really interesting branch that's taking place. And these are the people leaving the field who are going to other fields and taking the toolkits, the knowledge, and the insights into other areas. And so people are now saying, what if we use our quantum information ideas? Can we solve problems that are outside of quantum information? And one area that's very hot at the moment is quantum biology. And so I put up this slide to show you the kind of activities. Some I like, some I don't like, but I'm not going to be negative, so I'll just tell you what they are. This one represents mutations in DNA. This one was actually, so if you ask the question, when did quantum biology first start? The answer is Erwin Schrödinger. He wrote a book in the 1940s, What is Life? And he proposed that the mutations could be driven by quantum processes. It turned out not to be correct, but it was good that Schrödinger proposed it because it was a valid question at the time that was later refuted. But the idea that quantum effects in a non-trivial way, so there's a trivial way of manifesting quantum effects in biology, and this is that biology is made of chemistry, and chemistry is described by Schrodinger's equation, and therefore all of biology is obviously chemistry, is obviously quantum. The non-trivial one is saying, let's work in a domain where we think we don't have to use Schrodinger's equation, we don't have entanglement, do those effects still manifest in a regime where we think they should disappear? And so Schrodinger's idea was the first of that sort. There's also work that goes on bird navigation. So it turns out that in bird navigation, somebody who works a lot on this, there's Vlatko Vedral, who's jointly at Oxford University and at the National University of Singapore. As an example, there are a lot of others. And the idea is that it turns out that there's this bird that some ornithologists study in Hanover, and they find that the bird is able to find the north-south magnetic axis, but not be able to discriminate north from south. So then you say, well, what kind of magnet does this bird have in itself that is able to discern the north-south axis but not know the difference between north and south? And through a complicated argument, the idea is that there must be a singlet-triplet transition in some molecule, and the magnet has to be large enough that it's sensitive to the weak field, and if the singlet-triplet transition involves entanglement, then it has to be a long-range entanglement. So they argue that. So far they found that when they pull out the bird's eyes, it can't find its way anymore. So in that horrible way, they at least found out it lives in the bird's eyes. But not a lot is yet known about what the mechanism is, but it's an argument that there's long-range entanglement going on inside of these birds. Another example that has, this is about coherence. Some people call it entanglement, but I disagree with the term here. And this relates to a particular bacteria chlorophyll that lives deep in the water, and it turns out that light is very scarce. So it has to have a very efficient way of being able to collect light. Well, the way it works is that in comes a photon, it hits an antenna, and then the light travels into a reaction center, and then it's converted to an electron, which is used for a reduction oxidation reaction, and this is a photosynthetic interaction. In standard theory, it's an irreversible operation. When the photon hits it and it goes to the reaction center, it's like a one-way transfer. But in a beautiful experiment in Fleming's group at the University of California at Berkeley, they found that there's what I, as a quantum optics person, think of as a Rabi oscillation. Same with a magnetic resonance person. So there was, instead of it just going there, there's evidence of a Rabi oscillation. Since then, there's been a lot of femtosecond laser spectroscopy on this system, and they're doing full process tomography on this to find out what's going on. But there's very beautiful quantum coherence, and quite a few people have developed theories based on quantum walks, which is a quantum information-inspired notion to explain what's going on. So this photosynthesis going on in a bacteria chlorophyll has a very nice interpretation in terms of quantum walks. So this is considered, this probably in quantum biology, most people who say they do quantum biology are working on this photosynthetic interaction. And then on the more extreme end, which I'll just mention, there's the stuff that Penrose is interested in. He's got a collaborator, Hameroff, who's an anesthetist based in Arizona. And in that one, the idea that they argue is that there's a quantum effect going on in the brain, which is related to consciousness. You could read Penrose's work to get an idea, but I'm not a fan of that. And this one is the whole idea of consciousness itself, which I'm not a fan of myself, but it started with Wolfgang Pauli in trying to understand the measurement paradox, so it's got a very respectable beginning. So these are 5 of them. There's actually more going on. I do some work myself with electron transport and protein complexes, but mine is still a fringe area at the moment, so I didn't put it in the set. So that's what's going on there. Another one I want to bring up, this one, so again, this is whimsical. Another area that turns out to be very interesting, so I kind of put this up to give you an idea of the artificial intelligence area, and it's the good and evil. Here's the Terminator, from the Terminator movies. This is the good one. This is from a Star Trek show. Some android who's sentient, sees his own head. And so the idea is that it's an area I work on myself too. It's the area is taking artificial intelligence and combining it with quantum systems. So it's quantum control, quantum systems, and there's some interesting questions that emerge by considering whether it's possible to control systems making use of intelligent machines, and what advantages are preferred by considering quantum-enabled intelligent machines. And then I want to mention this one. So Seth Lloyd has come up again and again in the discussion for the quantum simulation, and he had a book, and so you can read the book. I'm not on, when I mentioned Merman's book and Seth Lloyd's book, I'm not on commission, so it's not like I get a take if you buy the book. But Seth Lloyd wrote this book, it's a popular book called Programming the Universe, and it says a quantum computer scientist takes on the cosmos. And in the book, he argues that the universe is a quantum computer. And it's interesting to think about. I don't believe it myself. It's not my own point of view. But it makes you think a lot. And so he argues the universe is a quantum computer. And so it starts to make you think, what are the implications of that? And so in closing, my last slide, I just want to take you back to Feynman, who was the guy that I would say started this whole field. And I just wanted to take, it's a very old quote from Feynman, but it's a really nice one. And I think it connects with what Seth Lloyd wrote. So he says, I hypothesize that ultimately physics will not require a mathematical statement, that in the end the machinery will be revealed, and the laws will turn out to be simple like the checkerboard with all its apparent complexities. So Feynman, again, you have to do this, if anybody knows hermeneutics in religious studies, that kind of thing, you have to do hermeneutics off on what Feynman wrote. And so the idea, what Feynman is saying here, I feel is kind of away from the grand unified theory direction in theoretical physics and more towards the cellular automata interacting systems type of argument. And it makes me wonder if his direction in quantum computing and his particular interest in quantum simulation was really just a stepping stone towards trying to address some of the big problems of the universe. And that with Seth's book and the concept that the notions of the quantum computer could ultimately be important if we want to understand the biggest problems in theoretical physics, I think is very exciting, and especially for giving a talk here with the International Center for Theoretical Science, it's nice to end on a very big question. So thank you very much.
We should have some questions now. Feel free to ask away.
Why do we use 2 bits, not more than that?
Why do we use 2 bits?
Two-level system, qubit.
No, we don't. Okay, so it's a very good question. We don't have to use two-level system. It's sufficient. So if we use a higher level system, so if you consider that you have n particles in your quantum computer, and they're 2-level systems, you can work in a 2 to the n dimensional Hilbert space. If you had 3-level systems and you could manipulate everything, then you're working in a 3 to the n dimensional Hilbert space. The concepts of complexity, if we say, what does a quantum computer give us in terms of scaling, we don't care what the base is. It's a base of a logarithm, essentially, or a base of an exponent. However, if we care, we say, well, we could really only use 5 particles, and we could have higher dimension, then we want to make use of it. So in the shorter term, if we don't have scalability, then what you're asking could be important. There are examples. I mentioned the ion trap. In fact, in the original ion trap scheme by Sirac and Zoller, their scheme relies on 3 levels for the ion. And in other ion trap schemes, they have multiple levels. But the qubit is still a 2-level system, and other levels are used for control. In the superconducting qubit case I mentioned, I showed you a nonlinear potential, and then different levels, and I said we treat it like an effective 2-level system. There are, in fact, other levels. But so far, we think of the other levels as being bad news. They kind of decohere the system. The reason that we don't generally use 3 or higher levels is it's hard to do. If we say that we want to make a Hadamard, that R gate I wrote down in the C0, then you have to ask the question, what is the universal set of gates for more dimensions? And it makes it harder to demonstrate a working QDIT, as it's called. But it's a direction that a lot of people consider.
So it's about practicability. How practical?
Yeah, it's just a quite like, how it works in the academic world. People apply for a grant, they get it, they do what they think is most promising. There are people who think about this, and it's important, but there are many important problems, and that's one of them. But in the long term, we don't expect it to matter.
Just a related question. Have people used these 3-level systems to study spin one physics or something like that?
Okay, so have people used so people have used 3-level systems. I'll give you an idea of where it's used. In quantum information, there are various protocols, including quantum bit commitment, quantum coin tossing, which are not completely secure, and also quantum key distribution. And if we go to higher dimensional systems, people then try to make entangled Q-trits and so on. So if you look up experiments over the past decade, the purpose of doing the experiments is to deal with quantum cryptographic protocols with those. If it comes to dealing with a spin 1 system, that goes to the simulation area. then we can do it. But you can use two spin half particles also to work on spin 1, because you could do your Clebsch-Gordan coefficients. And so if you have two spin half particles, you can construct a spin 1 and a spin 0. So we could do spin 1 stuff, and people have written about it theoretically, but it's not necessary. It's a question of what turns out to be more practical. We don't have to deal with Q-trits to simulate spin 1, but it wouldn't hurt.
All the was it on?
I can hear you.
All the kind of what you spoke about, the experimental implementation of any sort of a quantum algorithm, and then the simulations part. Now the question which I want to ask is, does that itself reveal any other correlations apart from, say, entanglement? What we have used.
You're saying if we execute a quantum algorithm, does
that give us some kind of a back check on our theory itself?
So what you're saying?
Like, for example,
build a quantum.
Exist any other correlations apart from entanglement?
So you're saying do foundations of physics that way. You're saying build a quantum computer and test that.
What?
So people talk about this. I'm kind of not so positive. Remember I pointed out with Feynman, and I said that the reason he said that a classical computer couldn't simulate quantum systems, and he said certainly no, and he said the answer is the hidden variable problem, and I mentioned I don't agree with that. So I think some people have said if you build a quantum computer, isn't that a way of demonstrating the quantum mechanics is right? And my own view is no. I think that if local realism holds and the quantum computer doesn't involve some space-like communication, then I think that a local hidden variable computer is just as efficient. So I'm not sure, like, I don't see any way to use a quantum computer to test basic things like a local realism. You thinking about that?
Any more questions?
Sorry, can you wave? I hear a disembodied voice. Sorry, wait till the microphone comes too. Yeah. Okay, now I'm ready for you.
It's just a general question.
Yeah, ready now.
How is the energy conserved in a DC Josephson tunneling? Like it just came up during the lecture slide only.
How is energy conserved?
Yeah, in a Josephson tunneling. Like there's no voltage, but you get suddenly a current from one junction
from one
superconductor to another superconductor.
If I take let's say that I could change the angular momentum state of something, right? I take a photon and I have some atomic level and change it to another atomic level with different angular momentum. How would you say that angular momentum is conserved? Well, you'd say that a photon came in and carried it, right? So in the Josephson junction, when the energy is conserved. We believe energy is conserved. It's one of our basic principles. But sometimes when we write the equations, we write some things off as being classical entities, and then we kind of lose track of it. But I'm not sure which transformation you're talking about in the Josephson junction. But it's controlled electromagnetically. Is that what you're talking about, like the flux or something?
Generally, we take the relatively. There's a phase difference between both the superconductors at the junction. So we take the difference of their phase difference of their phases, and we say that there's a current arising from one superconductor to another superconductor. Like a current flows through the tunnel, through the junction. So, but still there's no voltage. So okay. So that's probably more technical than I want to go into here. So we could talk about it at a coffee break.
Last one. Yes.
So according to the hidden variable theory that you are talking about over here, I had question regarding that. Like in hidden variable theory, we say that we can only perceive them, but we cannot control the variables. Is it actually regarding that local realism? In local realism, when we go to measure the things, we lose some information about the system. So is it because of that fact that we cannot control the variables, we can only perceive them.
So I understand every word you said, but the idea of perception, I mean, I kind of use a very rigorous language in going through it. So I'm trying to translate what you say to my rigorous language, and I don't know what it means to perceive them, and I don't know what it means to control them.
No, means actually what the hidden variable theory is about. If you can just tell it.
Oh, you want to know what local hidden variable theory is?
According to local realism and hidden variable theory, how they are correlated to, means like controlling the variables or something.
Maybe we can continue this discussion over coffee.
Yep.
And we should break for coffee and reconvene again at 11:30. But before that, we'd like to offer this token of appreciation to Barry.
Thank you very much.
Thank